Hello. Thank you for joining us today for this joint webinar regarding Mender.io and IncludeOS. I am Drew Mosley with Mender. Joining me are Ralph Nguyen, also with Mender, and Ingva Vormestrand with IncludeOS. We'll start with just a bit of overview of system updates and why you might need them for your design. We'll briefly discuss some industry events to help motivate the need for updates and touch on a few high-level thoughts about why over-the-air is desirable. For clarity, if I use the acronym OTA throughout this talk and the presentation, that is a shortening of over-the-air. Then we'll dig in a bit deeper and describe the Mender product, including an overview of our approach to updates, some details on licensing, and some of the considerations that went into the system design. Additionally, we'll discuss a few roadmap items to give you an idea of what's coming up next. Then we will present an overview of IncludeOS, and we'll finish up with a screen sharing demo of both products and wrap up with any questions that are unanswered at that point. If you do have questions during the presentation, feel free to type them into the YouTube chat box. Ralph is monitoring the feed and will relay the questions to us. So, why are updates important? My guess is that those attending this webinar already have a good understanding of why updates are needed, but I think it's worth calling out a few items here. Patching security vulnerabilities is the most obvious reason for needing an update process. New vulnerabilities are discovered all the time, and it's becoming more and more important to be able to address these in a timely manner with software updates to devices that are already deployed in the field. Somewhat related to this is the deployment of bug fixes that are not necessarily due to security issues, but are due to other categories of issues. And finally, you might want to be able to enable new features for existing products that are deployed in the field. It's important to consider the cost of updates over the lifetime of products. If you do not enable OTA updating, then you will need to either have the devices shipped to a repair facility or send a technician on site for repairs. Neither of these options scale well in terms of either cost or time. Additionally, relying on end users to manually update their devices is not a good solution, as is evidenced by the number of consumer devices in the field that never get updated and continue to have the default passwords available and exposed to the wider internet. Finally, having a centralized update management server makes it feasible to maintain a large fleet of devices over their lifetime. For smaller fleets, you may be able to get away with a more ad hoc update mechanism. However, as the number of fleet devices in your fleet grows, so does the need for a more formal process. There have been a number of situations making news lately where critical vulnerabilities in consumer devices, such as home routers, have caused major internet outages. These kinds of attacks are becoming, sadly, more frequent due to the increasing number of internet-connected devices in the wild. The cost of these attacks are likewise increasing, and it is important that device manufacturers take a more active role in ensuring the security and safety of their devices after they have been deployed. If devices cannot be updated in the field, the cost of a recall, not to mention the brand damage from a large-scale compromise, can easily overwhelm most project budgets. The Internet of Things promises new features that consumers desire, as well as some that are certainly questionable. The number and types of IoT devices are growing rapidly, and just as rapidly becoming an attractive target for attackers. Malware, such as the Mirai botnet, is used to commandeer large networks of these devices in order to flood target networks with enough traffic to knock them offline. Other malware, for example, Wrapup, seem designed to counter such threats by preemptively taking these devices offline, rendering them useless. Device management using automatic over-the-air updates is a necessary first step in securing these devices. Of course, the update process itself needs to be secure. TLS should be used to ensure confidentiality when the contents of the target file system are considered sensitive. Cryptographic signatures should be used for integrity and authenticity, ensuring that only trusted images are installed. Finally, secure coding practices should be used for both the on-target client and the back-end server components. And finally, industry best practices for server management are vital in ensuring the security of the server-side pieces. So how does Mender handle OTA updates, excuse me. The basic approach is to partition the device storage into multiple root file system partitions, one of which is active and one is available for installing a new image at any given time. Additional partitions are added to support a bootloader and system data that is intended to persist between updates. Of the dual root file system approach is that you are protected from a brick device due to a broken update. This can help protect against buggy images, as well as update failures that are caused by infrastructure issues such as power failure and network connectivity. An alternative approach to updates is to use a runtime package manager to update individual packages. This is the approach used by most desktop distributions today. For embedded development, this is suboptimal as it makes it difficult to know exactly what software load is on each device. Additionally, conflicts between user-enabled changes and the updates provided by the system developers are difficult to predict, and the size of your test matrix can explode if you try to capture all possible permutations that can result from this. Using full image-based updates gives you full control and traceability of the installed software loads across your fleet of devices and can simplify the maintenance of your fleet. You can even go a step further if your use case supports it to make your root file system read-only, thus guaranteeing you know exactly what is running on any given device. The Mender updater includes both components needed to properly deploy a system updater: the on-target client software that manages the device and installs updates, and the management server and infrastructure to easily deploy this in a server environment of your choice. Both components of the Mender updater are available under the Apache 2.0 license, which means that you can use it and modify it as needed for your environment. Our engineering team develops both components in tandem to help ensure a solid, well-designed system. We use continuous integration to help reduce the number and severity of issues in our code base. Additionally, Mender is built using a microservices RESTful API, which allows easily customization for your specific needs. If you need customized authentication, for instance, simply code up a custom service that conforms to our authentication API, but implements whatever specific customization you have for your system, and you're ready to go. IncludeOS has used this approach to implement a custom client that can easily talk to the Mender backend. In discussions with embedded Linux developers, security and robustness are the primary characteristics they focus on when evaluating update technologies. All communications between the client and the Mender backend are, by default, encrypted using TLS. Additionally, the images output from the target build system can be signed using a private key that is known only to the developers. This approach allows a decoupling of the images themselves from the infrastructure and systems used to deliver the images. As mentioned earlier, the dual root file system approach is designed to ensure devices are not bricked by providing a fallback in case of issues with the installed update. The old system is still available in case there are issues, and the system will automatically roll back when needed. Additionally, custom integrity checks can be performed during installation of a new image to catch issues that are unique to each use case. Finally, the impact on your device users should be minimal. The update process runs completely in the background, and your device is operational until the install is complete and it is time to reboot into the new root file system. Looking forward a bit, delta-based updates is one of the major features that we're currently looking at. Currently, the images are compressed, and depending on the contents of your root file system, you may see as much as a 50% size reduction from the compression. In future releases, we're hoping to do better than that by leveraging the redundancy from release to release and transferring only the bits that have changed. The full details of this are still being worked out, but this is expected to have a positive impact on data usage as well as download times. For users with expensive and/or slow networking connections, this is an extremely desirable feature. Another coming attraction is the ability to use the Mender infrastructure to deploy images to other devices in your network. The Mender client can be installed on an embedded Linux system in your local network that can communicate with the Mender management server. The Linux system in this case will act as a proxy for sensors and other small systems and deliver updates using the standard Mender API and workflow. Other systems that are running RTOSes or bare metal code that may not have the the horsepower to run the full Mender client and protocol can then take advantage of the robustness and update capability of the Mender update system. So far, we've been discussing the Mender system as it exists today. The server is distributed as a set of Golang microservices that can be deployed on premises. We publish Docker containers to the Docker Hub that you can easily deploy in any Docker-enabled setup you may have. This gives you the flexibility to use existing server infrastructure and roll out the system as it fits your environment. Our next big step is to roll out the Mender server as a service. This will allow developers who don't have server-side expertise or simply who don't want to manage this all themselves to outsource that burden to us. This reduces the workload for Mender users and allows development teams to focus on their unique expertise. This will allow project teams to get to market faster since the Mender server components will be ready to go and not add anything to the development time. Looking out a bit further, we are considering how to add vulnerability management and scanning into the mix. Since we already have access to the images, it should be reasonably feasible for us to scan them for known vulnerabilities and provide feedback to users to help them develop better, more secure devices. Okay, so that's the basic overview of Mender and the roadmap. Ralph, do we have any questions that have come in before we hand off to Yngve for IncludeOS?
No questions right now.
Okay, well, very good. Why don't we go ahead, we'll hand off to Yngve to give the overview of IncludeOS, and once he's done with that, then we can circle back around and pick up the demos.
Thank you. I am Yngve from the IncludeOS open source project. We are a bit different from other operating systems. Here is a quote from our founder: "We will be the obvious operating system of choice for all single-purpose computers." And this is really important. We are not a competitor to Windows, and we are not a competitor to Linux. This is for single-purpose infrastructure type of products, like web servers or load balancers or firewalls or API servers in a REST architecture. So we don't have any CD-ROM drivers. I mentioned that the IncludeOS is a unikernel. And what is a unikernel? Traditionally, you have had applications and operating systems, and these have been very separate. There have been layers of separation between them. In unikernel, we do this. They melt together into one single entity. And why is this beneficial? In a traditional application, your application is the small part on the top left there. And it depends on a lot of libraries. And underneath there, you have an operating system with a kernel and an IP stack and device drivers and an operating system. This results in many moving parts, and things can end up getting out of sync. You could end up having the wrong library, or a driver could be missing, or there could be a vulnerability in a driver that you're not even using. So in a unikernel, we take everything we need, but only exactly the parts we need, and build it into a single image. You have your application code, you have the drivers you need, and only the drivers you need, and the libraries you need, so you end up with a really small image. We are talking in the order of about 5 megabytes, not gigabytes, but 5 megabytes. And this gives a lot of benefits. It's obviously more secure because you cannot attack what isn't there. As I mentioned, we don't have a CD-ROM driver because in a data center, there are no CD-ROMs. Also, the maintenance is very low because we are talking about really small images. I mentioned 5 megabytes. So doing a whole new image and transferring it is really simple. And you don't end up with a situation where you have upgraded your library, and that depends on upgrade the application, and things get out of sync, like in the traditional DLL hell from Windows, because you can upgrade the entire application. And this is obviously very resource efficient. IncludeOS is built in C++, which is famous for its zero overhead principle. This gives really, really efficient code. We have boot times that is measured in milliseconds. Yes, milliseconds. And C and C++ makes it possible to use hundreds of thousands of software libraries. Most of them are just a simple recompile away. Here is an evaluation that was done by some researchers from Cambridge and Harvard. They took an existing PHP application and recompiled it and ran it under IncludeOS. And I don't know if you can see it on your screen, but as you can see, the leftmost is IncludeOS, and it's really, really, really a lot faster. And the way this works with IncludeOS is perfect for using with Mender, because we can transfer a whole new image when we need to do updates. The way this works now is we have a current artifact. Let's say it's a web server. And then we connect to the master, which is a Mender server, and check, do you have any updates for me? And yeah, there was an update. So we download that into an unused area of memory. Then we store some state, because it's important to be able to restore without the user noticing that we updated. So we store the state, and then we reboot into the new kernel. We restore the state, resume execution. This happens in about 5 milliseconds. So most users don't notice a thing. This has been a bit of a worldwide tour of IncludeOS. There is a lot more information over at includeos.org, so you could go there to check it out. It's open source, and you can try it out. And we will show you a demo after Mender here. So back to you, Drew.
Okay, very good. Okay, very good. Okay, let's see. Ralph, can you make me presenter again? All right, very good. So
Sure
what you're seeing here, this is the Mender dashboard, primary interface of Mender. You'll notice here that I've got 3 devices waiting authorization. This is what I mentioned in the presentation about authentication. Devices that want to connect to your server right now, the default setup is that a user has to manually authorize them. Obviously, that's fine for a demo environment, but for your deployed system, you'll probably want to implement a customized authentication API to help automate some of this based on known good devices and such. So in my case, I'm going to go ahead and authorize all 3 devices. They'll take a minute, and then on the next check-in from the devices, they'll send a bit of inventory, including the device type, current software load, that kind of thing. And you see here that we've got a number of bits of information that came. In this case, this is an emulated device running QEMU. This is part of our development environment. If you download, we have an integration environment that's a Docker Compose setup that you can download and deploy this yourself. Usually takes about 15 to 30 minutes to get it all up and running if you wanted to start playing with this. The inventory fields are a set of key value pairs. They're very easy to expand if you've got additional data that's relevant for your particular design. In the demo environment, obviously, it's just the generic devices, the kernel version, the IP address, the MAC address, that kind of thing. So this is fairly easy to expand. Additionally, you'll notice in the artifact screen, these are various images that I've uploaded ahead of time. And in my case, what I'm going to do is I'm going to go back to the device window, and I'm actually going to create a group here. This kind of simulates a phased rollout. So I'll create a group of early adopters, and I'm only going to put 1 device in this. I'll put the BeagleBone in this group because it tends to be the fastest for demo purposes. So once I have the artifact, I have the devices I want. It's time to do a deployment. So we create a deployment. I'm going to pick target image 1.1, deploy it to the early adopters group, and let it run. Now in this case, In a minute, it'll switch from pending to in progress, and then we can pull it up and see the status of the device. Or excuse me, of the deployment, not of the device. So this will take a minute to run, and I can tell you right now that this particular image is designed to fail. So what you will notice is that the device will reboot, and then the deployment eventually will be marked as failed, and it will have rolled back to the existing current software load, which in my case is target image 1.0. Now, normally this takes a few minutes. While we're waiting for that, Ralph, does anybody have any questions?
No questions so far.
All right. Well, while we're waiting for this, it'd be a good time. If you do have any questions, feel free to type them into the chat, and we'll do our best to address them. Right now, my BeagleBone is rebooting. The boot has failed. It's rebooting again back into the 1.0, and in just a few seconds, we should see this deployment go into the failed state, and then we'll note that the software load has stayed at target image 1.0. Okay, my device is finished booting, and as soon as it talks back to the server, we'll notice the status again. As I mentioned, it is deployed failure. Nothing interesting. All I did was set that target image 1.1 to immediately reboot before doing anything. Now we go back into the deployment. I have the fixed version in target image 1.2. Again, go back to the early adopters group just like we did before, and we create the deployment, and we wait a few minutes, and then this deployment will succeed, and we will have successfully updated our device over the air. All right. Now, while we're waiting for that, Ingva, do we want to hand off back to you for the IncludeOS demo?
Yeah, we can do that.
Okay. Very good.
Okay, so what we have here is the dashboard from a web server that we developed at IncludeOS. And as you can see, we have lots of information here. We have a CPU usage chart, we have a memory map, we have some information about the instance, we have TCP connections and everything. That's not what we're really interested in here. Now we are going to demonstrate how we use Mender. And if you see this CPU chart here on the top left, you can see that it's basically random. So this is clearly a bug. We need to upload a different version, but we don't want to take down the server and have a lot of downtime. So obviously, we just use Mender. Here you can see our dashboard, and we only have one instance here, but that's enough. We create a deployment. We have an artifact ready here. We create a deployment, and we go back to our dashboard. And as you can see, the update has already happened. We are now running a fixed version, and as you can see, our active CPU is now near 0, and we have a lot of CPU capacity to spare. And the actual update happened in about 5 milliseconds, but obviously we cannot connect to the Mender server quite that often, so it takes about, I think we check every 10 seconds for an update, and if there is an update, the actual update happens in 5 milliseconds. Now, in the rare event that something went wrong, we can actually go back to the previous version. We don't really need rollback, we just live update to another instance. So if we go back to the Mender dashboard, select our instance, and we can create a deployment. Now we go back to the one we used before. We create a deployment, and we go back here. And we wait, and there you see, now we are running the old version again. Again, the actual update takes about 5 milliseconds, but because we wait for update notification from Mender, it seems to take almost 5 seconds, which seems very long, but it's pretty good. And that's actually the workflow we are trying to enable with IncludeOS. We want to be able to update a running instance so fast that basically nobody noticed that it has been updated. Back to you, Drew.
Excellent. That's a great demo. Thank you so much. And I just want to go back and now we can kind of wrap up the demo here of the actual Mender demo. At this point, it's kind of similar to what you just saw, but just to make sure that I wasn't pulling your leg before, we now see that the deployment status has succeeded for that target image 1.2. And if we go back to our device inventory screen, you'll see that the BeagleBone device itself has been updated to the 1.2 image. So in this case, we did both a failed update that automatically rolled back, and then did a successful update to deploy a fix for that issue. So everything worked out as we expected. So I just kind of want to wrap up by mention just a couple quick things. Obviously, with the Mender project, one of our design goals has been to be expandable so that we can easily complement existing projects. Obviously, IncludeOS is an example of that. And Ingve, I just wanted to kind of throw to you for a second. You had some unique technical requirements. Obviously, you couldn't run our client as is. We require Golang and a few other things on the target that may be a bit heavyweight for your system. So in your case, you actually made your own client, correct?
Yes, we made our own client in C++, but obviously there was a lot of really good documentation and example code from the Mender repo. So that was surprisingly, I wouldn't say simple, but less troublesome than usual development problems.
Excellent. That's good to hear. Yeah, that's we work hard at making sure everything's well documented and easy for folks to get involved in. We do have a fairly active community. We're happy to take community contributions of features and ports and that kind of thing. So if you go through our website, you can find links to the mailing list where you can get involved at that level. You can find links to contact us for more information. And as I mentioned, you can find the links to actually download the demo environment to deploy locally and start playing with it on your own. So with that, I want to thank everyone for your time and attention. I will open up the floor if there are any questions. We can hang out for a few minutes in case anybody has any questions. So if you do, feel free to type them into the YouTube live chat box, and we'll do our best to answer them. And Ralph, I believe that we have contact information if they want to contact us with questions offline. Is that correct?
That's correct. If anybody has any follow-up questions to the Mender team, feel free to send us an email, contact@mender.io. And if you have any questions about IncludeOS, Ingve, what's the best approach there?
You can also send me an email at ingve@includeos.org, or you can go to includeos.org and look at the documentation. There's a link to our blog and to chat. So we are pretty easy to get hang on.
Excellent. So it doesn't sound like there's a whole lot of questions coming in. Ralph, should we hang out for a few more minutes?
Sure, that makes sense.
All right, and while we're waiting, I'll just mention a couple other things. I did mention that we, on our website is links to the mailing list if you want to get involved at that level and start playing on your own and maybe port to your own platform. Porting Mender to an existing platform is a fairly straightforward affair, as Ingve has indicated, and they even went a step further than most users. So if you have your own custom platform, feel free to jump over to mender.io and check us out, and drop us an email, and we'll do what we can to help get you up and started. And with that, I will say thanks again for your time and attention. Thank you for attending, and everybody have a nice day.
Thanks, everyone.
Yeah, thank you.